Today we are showing how to increase a VLF loop sensitivity by resonance. Here is how it works with simple, inexpensive components. An efficient antenna is crucial for clear reception. The English time signal isn't easy to receive here in southern Germany, as it's primarily intended to cover England. But look at this, my indoor loop is receiving a strong signal with good signal-to-noise ratio. Our DIY antennas are achieving respectable results, even when your location isn't ideal like mine. In our playlist Antennas and Wave Propagation, we are explaining their working principle, and in addition you will find tips and tricks to avoid interference. Although the previously built VLF loop antennas are very effective, they can be further optimized. Incidentally, there is also enormous potential for you here. With your own PCB, your project becomes replicable and resilient. PCBWay is offering some great new deals this holiday season. Just go to the company's website and grab a special offer. Besides PCBs, there are interesting options for casing, 3D printed or made from metal. And it's getting super exciting at the PCBWay 8th Project Design Contest. Maybe you would like to participate. Take the easy way with PCBWay. The open circuit voltage of a loop depends on the electromagnetic field strength, its area, the number of turns, and the wavelength. Its impedance is quite low in the VLF range, as you can see from this diagram. As explained in previous videos, a simple loop is becoming an effective VLF antenna together with a suitable transforming balun. However, as we will see in a minute, its sensitivity can be improved even further. The 6-meter loop with a 2-meter diameter, shown several times, is to be improved as an example. Corresponding to the orange line, its impedance is approximately 0.5 to 1.5 ohms in the 10 to 30 kHz range. Next, we will investigate the elements that make it up in detail. According to the textbook, the radiation resistance depends on the fourth power of the wavelength, the square of the geometric area and number of turns. Oops, at 20 kHz it's only 6 pico-ohms. Loss is depending on conductor length and material. In this example, it's 36 milliohms or a bit more when considering the skin effect. The loop's inductance is 1.1 ohms, dominating the impedance by far. In other words, the maximum current we can draw from the antenna is primarily limited by the inductance. Reception tests with parallel loops confirmed a few dB more signal. There was an error in the last video. Using 2 loops not only results in a stronger signal, but also in a higher SNR. I just confused the columns. Kudos to the sophisticated viewer giving me the hint. In the previous video, we also examined wide conductors, showing that there are physical limits to reducing inductance. Wouldn't it be great if we could somehow compensate for the loop's inductance? Let's look at the Phasor diagram to see how this might work. Non-reactive resistance is on the horizontal, reactance on the vertical axis. Radiation resistance is non-reactive, but so small that it's practically invisible here. The copper wire is adding 36 milliohms. And now comes the loop's inductance of 1.1 ohms, skyrocketing on this scale. Let me switch to a 50 times larger scale to show how the impedance is derived. I'm going back to the small scale. The trick is to compensate for the loop's positive inductance with a negative capacitance. A capacitor naturally has losses, which I've simplified with the series resistance. In addition, there are contact resistances, which I estimate around 20 milliohms. The loop's impedance is reduced to 0.1 ohms. It's now determined by its loss and radiation resistance only. For implementation, we need to consider that the balun is adding its inductance, pushing down the resonance a bit. The smaller impedance at resonance allows for an 11 times stronger current, corresponding to a 20 dB stronger signal in theory. In practice, you need to take into account the following. A resonant circuit is behaving like a mechanical pendulum. With strong coupling, it cannot reach greater oscillations than the excitation. Tapping it too weak, it would only oscillate slightly due to its friction loss. The optimum, where it's swinging with great amplitude, is somewhere in between. Here is the analogy to the antenna resonant circuit. The optimal signal strength can be tuned via this coupling capacitance. Magnetic coupling would be possible instead, but a capacitor seems more practical to me. The inductance of the loop plus balun is roughly 10 microhenry. These are some interesting frequencies and the corresponding capacitances for resonance. Next, I defined capacitances that could connect in parallel as needed to achieve specific values. For a test, I soldered inexpensive capacitors onto a board along with switches. And then the array is simply connected in series with the balun and the loop. At its lowest resonant frequency of 10 kHz, the sensitivity is significantly increased over a bandwidth of 4 kHz. While successively switching off capacitors, the resonance peak is moving upwards in the spectrum. Very nice. To prove the advantage when receiving real signals, I need to make a comparison. My reference loop is receiving the British time signal MSF Unthorn with an average signal level of -107.1 dBm. With about 800 nanofarad in series, the resonance is at 60 kHz and the signal strength is increasing to -95 dBm. Using a coupling of 47 nanofarad yields the optimum signal of -91.2 dBm. That sounds almost like magic. We started with the non-resonant VLF loop as a reference. Then the resonant loop without coupling capacitance achieved 12 dB more signal. And finally, the resonant loop with the optimum coupling is outperforming the reference by almost 16 dB. And, always important to mention, The SNR is improving by more than 13 dB. I also tried a pure capacitor solution that's common for resonant shortwave loops. It's working for me in the VLF range too, but here the transformer is beating it, probably due to the extreme impedance ratio and limited Q factor of the components. The resonant loop has a decent advantage even with cheap components. I'm estimating a Q factor of 10 for my loop's resonant circuit. With high-quality materials, 100 or even 500 should be achievable, resulting in 20 dB additional sensitivity. Along with other measures, I'm looking for better, still affordable capacitors. Feel free to share your ideas in the comments below. Based on this, I'm planning a small rotatable indoor antenna. Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.